Hello and welcome everyone. Today we continue exploring cube action systems. And since you watched and liked all my previous videos, you are familiar with the doubling cube, cube action theory, cubeless and cubeful equities, and how everything ties together during bear-off. And if you didn't, let's assume Santa dropped cubeful equities down the chimney and move right into the next chapter, generating the test suite. I'm a firm believer in direct testing, which means, in this case, letting competing heuristics play a large number of games and judge performance by counting points won and lost, and not from arbitrary statistics, which are easy to cherry pick and difficult to combine into one definite answer. I too make arbitrary decisions and rely on some statistics, but direct testing gives me greater confidence in the results. And to pull it off, we need A set of positions to play, and B, a high-level player who will establish a baseline for comparison. We prefer B because each imperfect system has a unique style, and that complicates assessments of overall strength. A highly skilled evaluator, superior to all candidates, can significantly mitigate the impact of style. So Santa, the strong neural net I developed, will take care of ranking once we create the test suite. And it's not that easy. The space of all race positions is huge, about 1,000,000 billion. So we should focus on positions likely to occur in your games. My research is academic, but we are, after all, testing methods intended to help you over the board. So positions should come from actual play. My set comes from cubeful games played by GNU-BG, played from the start position until the first break of contact. I'm using a rudimentary cube action model I developed. I wanted a decent and fast player, not super strong necessarily. I mainly wanted to discard games that reach an obvious double drop during contact, and keep only positions who reached pure race. And you might be surprised to learn that less than 1 in 4, 24% in fact, survive. 3 out of 4 games terminate with a double drop, at least with my model. However, and here I'm going to jump the gun a little, only 15% of those get into the dataset. That's right, 48 games out of 200 reach race, and only 6 of those enter the test suite. Why? Because most games, 93% of them, reach race with the cube turned, and many of those are lopsided, that is, with the side holding the cube a severe underdog, and playing out those positions is counterproductive. There's no real decisions to be made. All half-decent formulas, and semi-decent humans, would agree on no redoubles until reaching bear-off, and so those cases don't add information about the cube handling ability of players. Contrawise, they actually mask the difference in strength. If Julie is a 3-to-1 favorite in critical decisions, and you add 96 trivial cases, her advantage shrinks to 51-49. So we play 33 games to get one usable position. And that takes much huffing and puffing from my old laptop, which explains why I collected only 550,000 of them. It's not a lot compared to a quadrillion, and since non-bear-off race lasts about 6 moves on average, the players get evaluated on making just 800,000 decisions. Not enough for a clear-cut conclusion, but large enough to get useful results. We use the test positions the same way we did for bear-off. Positions are played out twice. Each player gets to play both sides with the exact same dice rolls, so all players get the exact same decisions, and points won by each player are added to her running total. Note that by position, I mean both checker placements and the cube state. It's important because the cube is owned 2 times out of 3, so redouble handling is more important than doubling. There is, however, one important difference from bear-off testing. Each position is played only until bear-off. If the game terminates before reaching bear-off, great, one side gets the full value of the cube. If not, the value of the current cube is split between the players to reflect the equity. Here, for instance, black started with a 2 cube, redoubled somewhere along the way, and ended up here with an equity of 0.62. So black is awarded 2.31 points and white 1.69. 1.69 and 2.31 add up to 4, and their difference is 0.62. Games are played till bear-off because we're focusing on race cube actions and don't want to conflate them with bear-off decisions. We can award fractional points with confidence because bear-off equities are exact, and doing so has the added benefit of reducing the variance, something which compensates somewhat for having less data. So let's get going and kick off by throwing our 5 bear-off champions into the fray, as is, without modification. And add the simple 8, 9, 12 as well, to ensure that pip count only methods are hopeless in general, not just in bear-off. And these are the results, expressed as ELO in this funny game against Santa, this short game which starts at some race position and ends when reaching bear-off. So the numbers convey rank and aren't directly related to other backgammon ratings. Funny game, but interesting results. Remember how in bear-off Isight was last and pep count was firmly above it? Well, here Isight is a close second, and pep count struggles. Not a big surprise. Pep count was designed for bear-off and uses a difference in born-out checkers to adjust the pip count, and that's 0 in most race positions. Thorpe and its descendants prove that adjusting for gaps and wastage is actually much more important in race than in bear-off, something I still find counterintuitive. Also, the ELOs are quite close, and it's prudent to check if the differences are statistically significant. So here's the 95% confidence intervals. Informally, confidence intervals give the idea of the variance, what the value might have been should we run the experiment a second time with different randomly collected data. And when intervals overlap, it's harder to claim one method, which won more points, is better and not just luckier. So here, we are quite certain that Keith and Isight are better than the others, and Ward and Thorpe are better than pep count, but unsure about the status of Ward versus Thorpe and Keith versus Isight. Fortunately, it's not that important, because we won't be using the bear-off versions. We want the best possible race versions. So let's look at 3 key aspects: count augmentation, doubling windows, and usability. And they all interconnect. But let's do them one by one. It might get confusing anyway. So, as you remember, each method is split into 2 stages. First, compute a number which represents how much black, on roll, leads the race. And second, apply some criteria to map said lead into a decision. I keep the method names for familiarity, but they actually represent just the counting. The mapping criteria comes from my own research and was optimized for bear-off. So we should examine both stages for possible improvements. And for the first, counting, there's one concept which has been around from time immemorial. It even appears in the Old Testament: crossovers. Crossovers are mentioned in connection to move selection and pip counting, but nobody knows who suggested using it to adjust pip count in race formulas. The mathematician Douglas Zare summed up the issue nicely in 2003. Are crossovers bad? It sounds like they ought to, but how come they aren't already accounted for in the pip count? Let me illustrate with 2 examples. Here, black leads by 5 pips, and is level after adding 10%, so aggressive systems like Isight are happy to redouble this no-redouble position. Indeed, if we shift the 2 outside checkers inside and move back 2 inside checkers, we get a position with the same pip count, which is a redouble. However, typical play is not that efficient. If we say give black and then white a 4-3, we reach this position which remains a no redouble. So crossovers do generate some wastage which impedes bearing of checkers. Here's another example, where black is stronger than unadjusted pip count suggests. Again, if we bring white's outside checkers in and move back appropriately, the resulting position is on the cusp, an optional take or drop. But actual play is again less efficient. In fact, black will reach bear off with at least 5 pip advantage 5 times out of 9. And they are all drops. And even when black's race advantage is smaller, 1 out of 5 positions is still a drop. So crossovers, which create wastage, do matter. And I pottered around with various ways to adjust the pip count according to crossovers and found nothing new. The simple and naive way is better than any advanced idea I tried. Simply count the total number of crossovers and add to the pip count. Here, white's count is increased by 3 and black's obviously stays the same. So, after much checking, this is the updated leaderboard with the best adjustment for each method. Turns out, Keith is good as is, but the others gain by adding 1 pip per crossover, and pep count even needs 2. So everybody except Keith improved by 2 to 5 elo points, which is quite a lot for values between 10 and 20. And since I'm not aware of any other generic adjustment, let's jump to a very different topic, usability. And by usability, I mean ease of using methods over the board, or even online. One reason I like pep count, which I pointed out before, is that it's easier to do adjustments differentially. That is, in pep count and in Thorpe, we start with computing black's pip count, then add 10%, and then subtract white to get the raw difference, usually getting a small number, and last adjust the difference by comparing similar black and white features. No need to add 11 checkers times 4 to black and 9 times 4 to white. We can simply subtract 8 in the end. In Ward, Isight and Keith, we must go the long way since inflating black's count happens at the end. Larger numbers and a longer process, which means more opportunities for mistakes or for forgetting the other count on the way. So I set out to see if it's possible to reformulate them to follow the same pattern without significant loss. It's possible, but obviously goes hand in hand with tuning the doubling windows, which need to be retuned anyway for S positions. This you might remember from the main figure in my last video, which showed how doubling windows change with the TTF, the time to finish, which is usually shorter in bear-off than in race. So here are the numbers for the best variants I found. Please note, I listed 2 Isight variants, Isight O and Isight Star. The Star is for the pre-inflate versions, and O is the vanilla post-inflate version. I entered both because O came out so very slightly better, even though the confidence intervals suggest they are basically identical. I marked names with a star to remind you those are modified versions, modified more than usual at least. And this table shows the modification for each, which we need to review in detail, but not today. Today, we'll finish with a delayed explanation and one example. Look at this plot. Each dot represents the agreement in cube action for our 6 players and Santa, 7 players in total, for race positions with the same cubeless win probability as given by the x-axis. So, for positions with 50%, all 7 players agree more than 95% of the time. But between 69 and 77, the critical range, it's less than 5%. This figure supports my decision to include only test cases containing at least one position in the range 60 to 84. And remember, the players get tested on the whole range. The positions you see here are from the test suite. It's just that rejected tests contain only positions outside the range, a string of easy decisions which muddy the difference in strength. And with that out of the way, here's an example from a recent game I happened to catch on YouTube. The score is 8 away, so should be similar to money, and Dawn stopped to consider cube action. The word count adds 2 pips for each checker on the board, 1 for each empty point, 2 for each checker above 2 on the 1 point, and 1 for each checker above 2 on the 2 point. And here's how word star might go in your head. 5 times 5 is 25, and 8 times 2 is 16, so 41. Subtract 1 and 1 for the imbalance to get 39. And that's the pip count in the home board. 2 checkers on 10, that's 20, giving 59. At 10%, 64. That's the pre-inflate. Note that I'm showing the single number you need to keep in your head during the process. Now, compute white's pip count. Really easy. 5 times 9, 45, plus 10, 55, minus 2 for the imbalance, 53, plus 13 for the outside checker, 66. So, black's ahead by 2. Both have 2 crossovers, so no need to do anything. Both have 15 checkers, again nothing. White has 1 more gap, so 2 plus 1 is 3. Both have the same number of checkers on the 2 point, again nothing. And now, deduct 2 points for black's extra checker on the 1. So black leads by 1 adjusted pip. Note again how we do everything by difference. It's easier and the numbers remain small. In vanilla world, you need to add 30 to the 59, then add crossovers and gaps, then add the 10%, and then do the same for white. More operations, bigger numbers, higher chance to err somewhere. Finally, word star is minus 103, so word star says double take. You might think this is a lot of brouhaha for an obvious double take. Maybe it's obvious, I'm not at that level. What I do know is that I have about 2000 positions in my test suite with a 59 to 66 pip count, and not all of them are obvious double takes. How about this? We know there are only these 2. Add 1 for white's crossover, 8 for bearing off 4 checkers versus none by white, and subtract 4 for black gaps. 7. A strong pass by word star. And it is a pass, but not as strong as word star thinks. And here, black has 1 more gap and 1 more crossover, so minus 2, and 3 checkers on the 1 point, another minus 2. Total minus 2, so no double take. And here, white has an extra gap, but that's the only adjustment. So word star says double take, but it's actually a drop. I could go on, but hopefully you got the point. It's not hard to compute word star of the board if you can master counting race. You can take word star advice or not. It's far from perfect, but I certainly need all the advice I can get. And even top players might find those opinions useful. And that's all I have for you today. How I built the test suite and how I progressed towards finding the best race cube formulas. And I'm sure you want to hear about the practical details and all the rest. And that's coming soon. Sooner if you like and subscribe. Adieu.